The broadcast is now starting. All attendees are in listen-only mode.
Hi, this is Rach Western from Gatan. Thank you for joining the webinar today. We'll be talking about using EELS and EDS together for spectrum imaging for doing fast mapping and analysis at the atomic scale. Before we get started, just a reminder, if you need to ask any questions, open up the question panel on your WebEx interface. If you have any questions related to connectivity, we'll try to get those right away. Otherwise, we'll have a question and answer session at the end of the presentation. Our speaker today is Dr. Paolo Longo, who's the Applications and Training Manager here at Gatan. Paolo joined us about 3 or 4 years ago now from University of Glasgow, where he studied with Professor Alan Craven. Paolo was one of the earliest practitioners of DualEELS, where they had a very custom system there for doing DualEELS, and were one of the founding groups, together with the group at Orsay, for doing DualEELS. So Paolo's been working in this field of multi-signal acquisition for quite some time. The presentation, we'll let Paolo just get started here on the presentation of DualEELS. Again, if you have any questions, please put them into the question box, and we'll get the question and answers at the end.
Thanks, Ray, for the introduction. I would like to welcome anyone. I would like to welcome anyone to this today's webinar, where we're going to talk about the EELS and EDS. How we can best combine both the techniques, and especially for fast mapping and also for mapping at atomic scale analysis. First of all, why high-speed? So the reason is because now we have bright electron sources. An example is the cold FEG, and also the X-FEG, which is enhanced brightness shock FEG from FPI. In the last few years, we're also seeing improvement in EDS detector with the silicon drift detector. They're actually increasing the number of counts and the efficiency. So now the lines of low energy can be easily detected. And more importantly, in the last few years, we have seen the development of faster EELS spectrometer like the GIF Quantum, where we can afford a spectral rate of over 1,000 spectra per second. So this is the overview of this presentation. Basically, we'll start off describing why we want to acquire both EELS and EDS. We're going to show the Gatan approach, so how we basically acquire both techniques. We're going to compare the two techniques. We're going to show some challenges for data acquisition, and we're going to also show some initial results. So why we want to acquire both EELS and EDS together? Let's look at these atoms here with electrons in the K shell and the L shell. So we have the incoming electron coming with a certain energy. This electron will lose some energy. Will promote one of the electrons in the K shell to an upper level. So now, two things can happen. These electrons are previously excited, can go back to the initial state, K shell, and emit an X-ray. Or you can go back to the initial state, and one of the electrons in the L shell will be emitted. This is called the OJ spectroscopy. EDS and OJ spectroscopy are basically like complementary, as well as EELS. But you can really understand that EELS probes primary event, whereas EDS and OJ will probe secondary events. So in general, X-ray is more favorable for heavy elements, whereas OJ spectroscopy is more favorable for light elements. This is the generation of signal in the STEM microscope. We have our specimen, we have the incoming electrons here that will hit the specimen, interact with the specimen. A lot of things will happen above the specimen and below the specimen. So if we look at all the phenomena that occur above the specimen, we have the generation of OJ electrons, we have X-rays that can be collected provided we have an X-ray spectrometer. And then at the bottom of the sample, below the sample, we have generation of secondary electrons, which can be collected, provided we have the detector. Some electrons that didn't lose any energy at all, so basically they just change their scattering angle, and this is called elastic scattering electrons. This will determine some diffraction, or can be collected to generate some like for example, like STEM images. And more importantly, we have inelastic scattering electrons. So basic electrons are lost and certain amount of energy. And the amount of this energy, the incoming electrons lost, can be measured using an EELS spectrometer. So if you look at all the X-ray, you can clearly understand that X-ray can be generated from every angle in the sample. The collection of signal is not efficient. So the detection of X-ray signal is inefficient for low and high energy. We have problems of fluorescence yield. So basically X-ray can be generated under X-ray. We have the formation or generation of scattering X-ray artifacts. And also we have problems with X-ray absorption. So basically X-ray can be absorbed by the sample itself. And this actually can prevent the quantification. So if you look at the EELS signal, you can clearly see that it's confined to a narrow cone of scattering. The collection of signal is extremely efficient, and provided we have a big aperture, so a big collection angle, we can collect most of the signal. And the quantification can be accurate. And we don't have problems with absorption. So why we want to acquire both EELS and EDS? So if we look at the composition, we can see that the EELS these days, with the latest generation of spectrometer, we'll look at this into more details in the next few slides, is uniform, the efficiency is uniform with Z. Whereas EDS, the yield varies with Z and is limited by absorption effects. EELS is actually very good at verifying unknowns. We can clearly tell the particular chemical phase in the sample, whereas EDS is good for identifying unknowns. So we can see what we have in the material, but we cannot see how whether these two elements are interacting with each other. So if you look at the thickness, EELS works very well with the thickness close to 0. And for thick sample, we have a rising background that can cause some problems. If you look at EDS, it works pretty well in thick areas of the sample. But if we use it for thin areas, basically we're going to have a very low amount of signal. We can do chemical analysis with EELS, so we can tell basically what we have in our sample. And now the elements are interacting with each other, are bonded to each other. In the case of EDS, we cannot get any chemical state information. But also in EELS, we can get additional information. We can get optical information, alloy, charge transfer, band gap, conduction, etc., plasmonic. Basically, we can fully characterize the material and basically get every type of information possible out of the material. In the case of EDS, a lot of information can be correlated only looking at the composition. So basically, it's an indirect way of getting a compositional information, chemical information about the material. So if we look at the Gatan approach, so we have some challenges here because the main thing is that the EELS is acquired in parallel as a complete spectrum, a single readout. The count rate in this case is very high. And in general, we have the count rate. We have about if it's going from like 1 million to like over 1 billion of counts per second. So it's a very huge amount of events that we need to collect. In the case of EDS, it's acquired seriously. It's a random series of individual X-ray. The count rate is low enough that each event can be stored. In general, we have much less events per second. So the challenge here is that we have to synchronize the EELS spectrum readout, the EDS counting, and beam positioning. These need to be synchronized within a few microseconds. And all these signals are generated from different hardwares. And in the case of EDS, is actually collected by different manufacturers using an hardware produced by different manufacturers. And you can really understand that if you go fast, you're going to generate a lot of counts per second. So the amount of data that we're going to transfer is going to be too big for software synchronization. So basically, it's the software that is taking care of the synchronization between the EELS spectrum without EDS counting and the beam positioning. So we have to basically move on to bigger platform like 64-bit where we can handle a much bigger data set. So easily we can exceed the memory limit for a 32-bit operating system. So this is our approach at Gatan. We basically synchronize EELS and EDS, EDS acquisition and the beam positioning using a means of hardware synchronization acquisition. So this is a schematic of basically what happens. So what we do, we set up our experiment using the Gatan computer. So we're going to set up a exposure time for the camera, whether we want to acquire the data in DualEELS mode or not. So this will be controlled by the Gatan computer through the GIF timing master. So at the same time, the Gatan computer will set up the beam scanning as well as the EDS. So you can see that the EDS will all the data acquired by EDS will be stored in EDS computer. So once we click start, we basically kind of disconnect almost the synchronization with the software. And we can see the camera will generate a pulse, which is basically a spectrum that will transfer all the way up to DigiScan. EDS system is connected with DigiScan, and while we have the beam sitting on one spot, the EDS detector will keep acquiring. So once we get the pulse, so the spectrum from the camera, this will be needed to advance the pixel, the beam, onto another pixel. So data will be stored on each single hardware and then transferred as a buffer onto the Gatan computer. This is called hardware synchronization. This is basically the best way of synchronize all this signal from these different pieces of hardware. Currently, we can support this on Bruker Esprit, GeoEDS interface, and NORAD 7. So provided you have one of these detectors, so we can have hardware synchronization. We can synchronize EELS and EDS signal in a STEM mode using means of hardware synchronization. This is some data that we took using the FEI corrected Titan with XPEG, and the EDS detector is basically the fourth quadrant. So, and GIF Quantum ERS, so this is basically data taken using state-of-the-art instrumentation. All the data, EELS and EDS, were acquired simultaneously in well less than 2 minutes. Very fast acquisition. And you get basically these beautiful maps where you can distinguish the layer of titanium from hafnia, germanium, etc. And clearly you can already see the better contrast that you get with the EELS signal. This again because we can collect most of the signal. So if we look at the composition, we always study since the beginning that you want to use EDS for heavy elements, EELS for light elements. Things are now different because with the development of the GIF Quantum improved by a lot the camera, the readout of the camera, the performance of the camera. So now we could get EELS data in a fast manner from high energy edges, so basically from heavy element. This is actually an example of data taken in McMaster University. So here is a particle of platinum and ruthenium. So the core of this particle is ruthenium. As you can see from this map, the shell is made of platinum. Data were acquired in DualEELS mode where we have a low core loss, where you see the ruthenium M45 edges right here, and the titanium L23 at 456. We also acquired with exposure time of 1 millisecond, exposure time of 80 milliseconds. We acquired the platinum M45 at 2100 eV, and the ruthenium L235 at 2800 eV. So you can see that with the 18 millisecond exposure time, we can clearly collect a pretty high quality EELS spectrum with a good statistic and a good signal to noise ratio. So even here on the ruthenium, you can clearly distinguish the two lines, the L3 and the L2 lines. And this map was basically generated using the signal from the ruthenium at 2800 eV and the platinum at 2100 eV. So you can clearly see the background is much more stable for this high energy edge. But again, this is to prove the efficiency of this quantum for GIF Quantum for high energy edges. This is another example. It's again a kind of more fancy example where we, from the same material, we acquired again the DualEELS data from the low to high two core loss acquisitions. So the one at low energy is basically started from 2000 eV, and we are acquiring the platinum at 2100 eV, and the acquisition at high energy is basically we collect the titanium K edge 4900 eV. You can see that all these edges were acquired with a relatively short exposure time, even actually the pre-high energy of the titanium edge. You can actually generate maps with the titanium of 5000 EV, titanium KH, and the platinum of 2100 EV. So again, this is to prove that now we can do EELS from high energy edges from heavy metals, and there's no need of using EDS only for these high energy edges of heavy elements. EELS is pretty suitable to characterizing these materials. So if we go back to EDS, so if you look at this schematic here, you can see that the X-ray, basically we have X-ray detector here, we have the incoming, we have the specimen here, we have the incident beam. You can clearly see the X-ray will be generated from a pretty large volume. You can get contribution from pretty much everything inside the column. The upper polyps, the specimen itself, other area of the specimen, the support of the specimen, the TM molder itself. So if you look at this example here, this is palladium gold nanoparticles. We have EDS spectra acquired across the entire region. This is basically some EDS spectra. You can see a nice gold line, palladium line, the other gold line. But you also see some copper. If you look at simultaneously, we acquired EELS. We have low core loss in the EELS mode. We have palladium M45 edges, 335 EV, and also the EELS high core loss, 2200 EV. So you can clearly see here the presence of the copper. So where is this copper coming from? If you look at EELS, there's no copper in this material, so the copper that we detect in EDS is basically coming from the copper grid. So these particles were dispersed onto carbon film and a copper grid. So the copper that you see in EDS here is actually coming from the copper grid. So it doesn't belong to the sample itself. So again, this is to show the spurious X-ray. This is something that you have to take into account, especially if you want to detect a sample that contains copper. So you might want to switch to different grid. Another example here, we have a STEM image. Looking at the STEM image, we have a lot of contrast in this image. We have these bright plugs, which basically contain heavy metals. In this case, tungsten. If you do EELS, and we get like a copper map, you can clearly see the copper is confined to these layers here on top. If we do the same thing in EDS, you can clearly see some copper also present on the plugs. I mean, this is actually not real. It's because high-tech material, like in the case of tungsten, will generate a lot of spurious X-ray. So again, this is something that you have to take into account. This again because the signal is not localized. It's actually a clear example. Again, we have EDS EELS using again the same instrumentation, the FPI microscope with 4-quadrant EDS detectors, GIF Quantum, compare nitrogen from the same material. You can see again the higher contrast of the EELS map against the EDS map. You see a lot of signal in the tungsten plugs. Along again for the same reason. It's because high-tech material generate a lot of spurious X-rays. So again, something that you have to take into account. Quantification. So if you want to do quantification using EDS, the main problem is absorption. So in general, X-rays are absorbed by the specimen, TM molders, and detector. Absorption effect in EDS increases with the thickness and with the presence of heavy elements in the sample. And in general, this absorption is actually pretty big for, it affects massively low energy X-rays. So basically these X-rays are not going to have enough energy to escape the sample. The solution to limit this absorption or to avoid the absorption is working with very thin sample and possibly tilt the sample towards the X-ray detector. And so basically in this way we're going to maximize the number of X-rays reaching the detector. In general, when we do quantification, we use, we'll talk about this in more details, but the absorption effects can be modeled. But we need to know the material. So if the material is not uniform, it's going to be really hard to model this absorption effect. And this is going to affect the composition, the quantification using EDS. So these are the situation. So right now in the market, we have, in general, two different configurations for EDS detector. So we have a single detector situation, where we have a single detector. So if we want to improve the quantification, it's always better to tilt the sample towards the detector, so we maximize the number of X-ray, and we reduce the absorption effects. Or we have the 4 detector situation. So here we have 4 detectors wrapping the sample. So here X-rays, we have pretty good efficiency for X-ray collection. But again, modeling absorption is going to be hard because each detector is going to see a different amount of X-ray. It's going to see different areas of the sample. So the best way is basically switch off 3 detectors and tilt the sample towards one detector. So if you want to get like a very good quantification, want to improve the accuracy of our quantification using EDS in the situation of 4 detectors. So if we compare EDS and EELS for quantification, in general, if you look at EDS, the composition quantification is obtained using the Cliff-Lorimer method, where we have is a relative composition, where we have the relative amount of element A, relative amount of element B is equal like a coefficient. This is a factor, it's called K factor, over the intensity of element A, intensity of element B of the particular feature for element A and element B. In general, what we need to know in order to work out the quantification is this K, which is called the K factor. And this K factor can be calculated theoretically or measured experimentally. And this again depends on the material and detector configuration. If you switch to EELS, this is the formula that we use for quantification. The N is not a relative amount, relative composition, but it's basically areal density. So here we're talking about absolute quantification. So here we're talking about a number of atoms and not relative composition. And this depends on, again, it depends on the IK, which is the intensity of a particular edge of a particular element that we want to quantify for a given collection angle, integration window, divided die low. So it's basically the intensity over the low-loss region, again over the same collection angle, integration window, and for multiplied by like a cross-section, again calculated over collection angle at the same integration window. So here the only coefficient that we need to calculate or we need to measure is the cross-section. And this cross-section can be calculated theoretically or measured experimentally. And this actually depends mostly on the material that we're using and also on the experimental conditions. So if you want to do like quantification but in an automated way, so if you look at EDS, the standardless K-factor method, so basically theoretical, depends on accelerating voltage, ionization, fluorescence term, detector effects contribution, solid angle, and atomic weight. The calculated cross-section will depend on the accelerating voltage, convergence angle, collection angle, and atomic weight. So it actually depends on less factors than the K factor in EDS. So this is the screenshots of what we need to from digital micrograph. It's basically the information that we need to import in order to do quantification using EDS. you can see that we need to know a lot of information about the detector. Basically the position, elevation, etc., specimen geometry, and also the detector itself. If we look at EELS, the only information that we need to know about the material for the experiment, for the quantification is convergence semi-angle, collection angle, entrance aperture. That's it. This is basically the experimental condition that we need to know in order to do quantification using EELS. These are all the information that we need to know in order to do quantification with EDS. So we need to be very careful in characterizing the detector in EDS. So we need to have all the information. So again, looking at quantification using EDS and EELS. So the main limiting factors of quantification using EDS are the accuracy of the cross-section, the absorption. So we learned already what absorption is. And in general, the X-rays are absorbed while they travel through the sample and by the TM molder and detector. And the absorption depends on the thickness and density of the specimen. And as we said earlier in this presentation, it's mostly low energy X-rays are affected by absorption effects. In the case of EELS, the limiting factors are the accuracy for quantification, the accuracy of the cross-section, which depends on the type of edge we want to get quantification from. It also depends on the choice of the integration and background windows, on the thickness, but the absorption is not a limiting factor in EELS. So this actually is something very important to take into account. So we can get quantification very accurately from heterogeneous material. It's something that is actually affecting EDS in the case of heterogeneous material where we have light and heavy elements. It's in the case of the sample device with the tungsten plugs. If we switch to sensitivity, we compare the two techniques. This is an example for a carbon elemental map. This is data again acquired using the system in Graz, where they have a probe-corrected Titan with X-peg and the 4-quadrant EDS detector, the 4 EDS detector wrapped in the material. And then we have GIF Quantum ERS. So if you look at the EELS map, you can see the presence of the spots for beam damage here in the carbon map. So we have carbon basically ejected by the material as a result of the interaction with the electron beam. If you look at EDS, on the EDS map for carbon, we don't see the spots. But the other interesting thing in EELS, we see a layer of like bright layer between the silicon nitride and the substrate. If you extract an EELS spectrum from here, we see the presence of carbon. So this layer is actually, it contains some carbon. It's actually pretty important information. The EELS signal is pre-localized, so if we have carbon here, basically there is carbon in there. And this layer of carbon is basically absent in EDS. So again, this is the pretty bad sensitivity of EDS towards light material. Detection efficiency. This data again acquired simultaneously using GIF Quantum ERS for EELS and the 4-quadrant EDS detectors. So we know that the speed, the acquisition of EDS spectra basically can go up to 100,000 spectra per second. But is fast enough? Is a good speed? So these are like two spectra, single spectra, acquired, both of them acquired with an exposure time of 2 milliseconds. So if you look at EELS, you can see like pretty big amount of signal. You can clearly see the nickel LH, the silicon KH, this is nickel silicide. And the signal actually, the signal to noise ratio is good enough that this spectrum can be used for quantification. If you look at EELS, we just see like EDS, we just see like a very limited number of counts. And actually, these data were acquired with pretty big beam current. So even if you can go really fast in EDS, you're not going to acquire any signal. Probably you're going to have a lot of spectra without any counts at all. So yes, you could go fast, but you're not going to acquire any signals at all. So chemical phase identification. This is some data that were taken in collaboration with the group of Port Elizabeth in South Africa. So these guys are interested in diamond to build devices, electronic devices, and they're also interested in studying the effect of ion irradiation, carbon ion irradiation onto the diamond. So they start from crystalline diamond. This diamond goes to ion irradiation, carbon irradiation. We have the formation of an amorphous layer of carbon. So basically, the diamond is amorphized to amorphous carbon. If you take an EDS spectrum from the diamond, here we see carbon line, carbon K line, we see copper. Again, if we take it from the amorphous carbon, right here on the right-hand side, we see carbon K again and copper. So we can't really distinguish the two phases. So we see carbon near, we see carbon near. This is as much as we can say about this material looking at EDS. We can see that there is copper, but the copper is actually coming from not the sample, but it's coming from the Omni probe. So this sample was prepared using FIB. So the copper is coming from the Omni probe. We switch to EELS. We acquired the data in EELS mode where we have low loss. And then you take a low loss spectrum from this region, the diamond regions. You can see the plasma shifted towards high energy. You see the presence of peak here, the peak at 23 eV, which is typical of the crystalline structure of the diamond. You move on to the other area where you have amorphous carbon. You see the plasmon shifting, plasmon change shape. We lose the feature at 23 eV. And here we have the plasmon shifting a lower energy. So different between these two materials. It's a different chemical structure, and also the fact that the diamond is highly insulator is fully sp3 hybridized, whereas the amorphous carbon has a certain content of sp2, which we can actually measure. So if we collect core loss, so this data will collect simultaneously with the low loss, you can see typical features. Look at the diamond, carbon KH for the diamond. We see the typical features of diamond. We don't see much pi star, the presence of the pi star peak. This is because the diamond is sp3 fully hybridized. You can see on the carbon, on the amorphous carbon, you can see the presence of the pi star. So there is a certain contribution of sp2 in this material. So we can use these two spectra for MLS fitting, and you can see that the interface, there's a mixture of these two phases. And we also measured the presence of, we measured the amount of sp2, and we saw the amount of sp2 was going from the amorphous carbon into the interface was decreasing by 65%. So this is the information that you can get from EELS. Again, you can fully characterize the material. You get optical information and chemical information. So now we show, go to the other part of the talk where we show some data. All this data in this first section were acquired in Graz, where they have a pro-corrected Titan, 300 kV. All these data were acquired. Keep this Titan with X-ray, 4-quadrant EDS detector, Brugger spray EDS interface, and EELS data were acquired in using the Gatan GIF Quantum and DualEELS mode. All the data were acquired in digital micrograph with the 64-bit operating system. This is something important to say, that the system in Graz is actually the only system in the world, the only ChemiStem system in the world where EDS data can be acquired in digital micrograph. So this is basically the best system to compare the 4 EDS data acquired using the 4 quadrants EDS detectors and EELS data acquired with the quantum digital micrograph. So we started with looking at palladium gold. So data were acquired in DualEELS mode, acquiring EELS high core loss from 1800 to 3800, exposure time 30 milliseconds per spectrum. EELS low core loss from 200 to 2200 eV, using an exposure time of 7 milliseconds. EDS is basically the sum of these two exposure time. This is the beam current. This is from one single spectrum, extracted from the center of this particle. You can see still like the gold, some gold here, the gold line, copper, and gold, the other line. Again, we've seen that the copper comes from the copper grid. We don't see any copper here in the EELS. But even if looking at the EELS high-core loss, even with the one single pixel, we can still see a pretty nice gold edge. It can be used for quantification. If we sum 168 pixels over these two particles, we have gold, palladium, copper again, but we know the copper comes from the copper grid. We have the palladium at 335 eV, pretty visible. Basically, we have palladium here on the shell. And we also see, looking at the high-core loss, we see gold. We also see the palladium at 3100 eV. This is to show the efficiency of EELS for high-energy edges. So let's compare the palladium map for EELS and EDS. Again, looking at this map, you can tell, yes, they'll give the same information, but you can clearly see that the contrast in EELS map is much higher than in the EDS. It is something that you might want to expect because we're looking at the palladium low energy at 335 eV. So you can plot the line profile across the same region in both maps. You can see the higher contrast, higher signal-to-noise ratio shown by the EELS maps. So if you compare gold map acquired using EELS and EDS, again you can see higher contrast in. Surprisingly, you see higher contrast in the EELS maps. You can see a lot of features, a lot of details, which are basically missed in the EDS map. So if you extract the signal from the signal and the standard deviation from this region, you can clearly see from both regions, exactly the same regions in the EDS map and the EELS map, EELS and EDS map. And you extract this mean signal, standard deviation, the ratio of these two will give you the signal-to-noise ratio. And you can see that the signal-to-noise ratio for the gold map obtained using EELS is twice as high. So that means that if you want to get a gold map with EDS that is as good as the one obtained using EELS, we need to increase the exposure time by twice, so increasing the beam current for the same amount. You can combine this palladium and gold map in color maps. You can see gold green, palladium red. Again, you see the higher contrast shown by EELS, but again, this map were not filtered, not mathematically treated. This is raw data. This is another example looking at a device. Again, this map are kind of similar. We see like higher contrast in EELS, but this is in the case of the beam damage, which in the carbon map, which can be seen looking at and the EELS carbon map, which is actually not present in EDS map. So EDS is not very efficient for light elements. The other interesting thing we can see in the EELS map the diffusion of gold going into the substrate, the arsenic substrate, and this diffusion is not visible looking at EDS map. So again, this to show the sensitivity of both techniques towards light and heavy materials. We also did using the same system in Graz with the 4 EDS detector. We did some atomic analysis. This is like strontium titanate, and the left-hand side is like raw data, and the right-hand side is filtered data. So if you compare the data were acquired with exposure time of 10 milliseconds per pixel and a total exposure time of 48 seconds, this is the beam current used for this phase. So we acquired this map in very short exposure time. So if we compare the EELS and EDS maps, we can clearly see the higher contrast in the EELS map for the raw data. We can clearly distinguish the atomic column of strontium and titanium. So if we switch to EDS, we can see where the strontium and the titanium are, but we can't really distinguish the two columns. Basically, there is too much noise in this data. So you have to filter in order to distinguish the titanium and the strontium columns. You can do the same in EELS as well, although there's no need. The raw data in EELS are good enough to show where the two elements, the two columns, two different atomic columns are located with respect to each other. And every time you filter, you basically average pixels together, so you lose a spatial resolution. We did also oxygen. Both maps don't really resolve the oxygen columns, but we can still see a crystalline framework in the case of EELS, which is completely missed in EDS. So EDS, we don't see anything at all. It's just noise, pure white noise. Again, to show the high sensitivity of the EELS towards light elements, as well as heavy elements now. So now we switch to a different topic. So now the data that I'm going to show you are basically data acquired at atomic level using the installation IBM, where they have a gel ARM200 operated at 200 kV, probe corrected. We call FEC. EDS data were taken using the dual Centurio detector with an area of 100 millimeters square. The solid angle as specified by the manufacturer is 0.98 rated, so it's pretty big EDS detector. Okay. EELS data were taken using a Gatan GIF Quantum ER in DualEELS mode in some cases. All data were acquired and processed using a 64-bit digital microscope. So we started looking at the interface between strontium titanate, lanthanum iron oxide, and lanthanum cuprate. EELS and EDS data were acquired using an exposure time of 5 milliseconds. EELS spectrum was acquired from 300 eV to 2300 eV, being current slightly less than 200 picoamp. It's actually a pretty big data set, a very big map, and it was taken all the data in just about 4 minutes, so very fast acquisition. So if you look at single spectrum, the single spectrum for EELS, EDS from the lanthanum iron oxide area, so you can clearly see the lanthanum M line. You see a little bit of the iron, but you see the oxygen. If you look at EDS, you just basically see very few lines, not much. So you have to sum over 176 spectra to see pretty nice lanthanum, iron, oxygen, and you get like a pretty nice spectrum for EDS2 where you can distinguish all the lines. So you have to sum 176 spectra to go from here to here. So these are all elemental maps. These are EELS elemental map. So if you look at each map, is basically show much higher contrast than the equivalent map obtained using EDS, especially for copper. If you look at the oxygen, we don't see anything in EDS, so you can still see pretty nice structure in EELS. If you combine all these maps in color, you get like a pretty nice EELS map. You can see elemental diffusion at the interface. You also see the presence of a double layer of copper. You actually see the diffusion of copper into the iron. So this column here is made of iron and copper. And this column is basically completely not visible in EDS map. And you can't really distinguish the two columns here. What you have to do, you have to filter. So you have to filter so you can distinguish strontium and titanium. Here you can distinguish the same thing in similar things in lanthanum iron oxide area. But again, you struggle to see the diffusion of the copper into the lanthanum iron oxide. Looking at the EELS, this show like a beautiful map. It's pretty amazing. With such exposure time, you get these pretty nice atomic maps. You see like very nice diffusion of copper into the lanthanum iron oxide layer. This is looking at this interface in more details, and basically we don't get any information in EDS. The information is completely missed. This actually is the key of characterizing this material, this interface. This is the reason why this interface doesn't show good electrical properties. So the question is, we've seen a lot. I showed you like a lot of cases where simultaneously data, EELS and EDS data acquired simultaneously. The question is, why you really want to acquire EELS and EDS data simultaneously if both EELS and EDS deliver elemental distribution and compositional maps? EELS map show higher contrast for both light and heavy elements, and in addition to compositional information, EELS is capable to deliver other information such as chemical, optical, and conductivity. So the answer is that we can simultaneously use EELS for mapping the chemistry and EDS for the elemental distribution. We can use EELS to get thickness and beam current information. Okay, let's look at the first example. So here we tuned the spectrometer. We looked at the same interface on the titanium lanthanum iron oxide, but we tuned the spectrometer in a way that we have more energy resolution. So as a result, the field of view would be shrunk to 500 dB only. So here we acquired the data in EELS mode. We have EELS color loss from 350 dB to 850 dB, 25 milliseconds. EELS low loss from 0 to 500 dB, 37 microseconds. EDS will be the sum of these two. And the energy resolution now is 0.75 dB. So with the presence of the low loss spectra, we can correct the foreign drift, and we can also remove the effect of pure scattering. So the reason why we wanna correct the foreign drift is because we can measure the chemical shift more accurately in this way. So if I start the spectrum from this interface, this is basically all spectra average across the entire region. We see like a pretty nice result: titanium, oxygen, KH, iron, and lanthanum. But the problem is that the strontium is out of the field of view. The solution is to acquire the strontium elemental map using the EDS and combine this map with the EELS maps for titanium, iron, and lanthanum. That's what we did. So we have a pretty nice map for titanium, oxygen, iron, and lanthanum using EELS. EDS map for strontium. We combine all these maps together, and then we get information on elemental distribution for all these elements. And we can see again the same information we saw earlier from the same interface. Diffusion, elemental diffusion. We want to go beyond that. We want to see what we have. So we come to EELS. These data were acquired with good energy resolution. If you extract EELS spectra from region 1, region 2, region 3, region 4 across the interface, you can look at the titanium. You can see pretty nice result. But titanium, you see all these 4 peaks, so you can tell whether you have titanium 3+, titanium 4+, and titanium seems to stay 4+ across the entire interface. So the titanium actually we see elemental diffusion. We see titanium diffusing into the interface, but the titanium doesn't change its coordination. So chemically speaking, the titanium remains unchanged. If you look at the oxygen, you can see the pretty big changing across the interface. But the most interesting information is that we get from the iron. So if you look at iron in position 1 here, you'll see iron. Position 2, not much. Position 3, we see iron. This is again to show the high efficiency of EELS, and again the EELS signal is very localized in this case. So we don't see any iron in position 2. Monolayer after, we see iron. But the interesting thing is that if we keep moving by another monolayer, we see the titanium, the iron line, the L3 line shifting. So all this data were corrected with the zero loss, with the low loss. It was acquired simultaneously. So what we see here is a true chemical shift. So it means that the iron is changing its oxidation state going across the interface. That's very important information. This again, looking at the low loss, so with the system with much better energy resolution, you can see differences there too. So here it's, again, this is the last example. This is some EELS and EDS data acquired in Glasgow using a pro-corrected ARM at 200 kV, GIF Quantum 965. Here they have EDS detector 60 millimeters square, and all the data were acquired in very short exposure time, 0.5 milliseconds. High loss from 350 to 2350 eV in DualEELS mode, so we also have low loss information, and along with EDS, pretty high beam current. This is a massive data set of about 8.5 gigabyte. EELS low loss, EELS high loss, and EDS. All data were acquired in adversarial mode. So this is a color map for the device, EELS and EDS. You see high contrast in EELS. You see the presence of the oxide layer in EELS. Right here, the directed layer, which is not visible in EDS. But the important thing is not the quality of these maps, but it's the presence of artifact. So we can see the presence of different contrasts here in the silicon substrate. And this is actually due to the presence of the shadowing from the tungsten plugs. Okay, so we also see another effect right here on this other tungsten plug. So what we could do, we could use EELS, the thickness map obtained using EELS to normalize the silicon and the oxygen map for EDS. So you can see that after normalization, the contrast disappears. So the contrast we were seeing here was pure thickness. And that can be corrected provided you acquire the data in DualEELS mode. Same thing with EELS. After the normalization, you can see that the contrast is almost gone, and also the contrast right here is gone. So all the extra contrast that was due to thickness variation. We can again compare the two maps. We can look at this region in more details. We can see the nice the layer of the oxide layer, which is again not perfectly visible in EDS. In summary, hope I've been able hope you enjoyed this presentation. I've been able to tell you, convince you that digital micrograph is currently the only software capable to acquire simultaneously EELS and EDS in a fast manner. When the spectrometer is well set up and digital micrograph is used as acquisition software, EELS delivers elemental with higher signal-to-noise ratio than EDS for heavy elements, with zinc cases for gold, platinum, and tungsten. The EDS signal is very delocalized. The copper that is present in the Omni probe or in the grid is always detected. Light elements are pretty tough to detect using EDS. And the nitrogen, if you look at the nitrogen signal, it's pretty well delocalized. There's also some big absorption effect. If you acquire the data in DualEELS model, we have the low loss along with the EDS. We can remove effect from the thickness from EDS and EELS. We can also collect additional information such as the beam current. We would like to acknowledge Professor Botton from McMaster University for providing the sample and access to the microscope installation, and Dr. Oliver from Nelson Mandela University for providing the diamond sample, access to the microscope installation, help set up the experiment, Kotliner to Graz for providing access to the microscope installation.
Thanks a lot for that very enlightening webinar. We have recorded all of your questions and have recorded this presentation. We will follow up with your questions via email. We thank you all for participating, and we will send out a link where you can download a recording of this presentation in the coming week. Thank you again, and have a wonderful rest of your day.